Okay, friends, part 3. Let's go through this a little quicker. Sorry, I didn't mean to make part 2 so long if you were watching that one as well. Um, right away, you'll notice that these look a little different because they have this weird number up here. If you haven't gotten to any of these in class, or if you've gotten to them and not known what to do with them, I wish you would have asked me because we did 2 or 3 days, I think, of just like straight practice. So here it is now. If you haven't gotten the word, but these numbers are actually charges, and so that this 1 minus up here is telling us that this entire compound has a negative charge on it. Let's talk about what that means here. So first, let's just count up our valence electrons like usual, right? I know that my nitrogen has 5. Each of my oxygens has 6. I got 3 of them, so that's 18 plus 5 is, what is that, 23? But then, what the heck does that charge mean? Remember, friends, electrons have negative charges, right? And when we have an ion, if you're thinking back to our atomic structure notes from 2 weeks ago now, if we have a charge on an atom or on a molecule, that means that we have an uneven number of electrons and protons. So when we have an even number, that's a neutral charge, right? Because all of the protons and all of the electrons are like canceling each other out. But if this is telling us that we have a negative charge on this molecule, it must mean that we have more electrons than protons. These numbers are based on atoms of nitrogen, atoms of oxygen. But if we have a negative charge, we must have an extra electron in there. And that's how, that's where that negative charge is coming from, I guess. So we need to take this 23, add 1 more electron, and get 24 total valence electrons. And so you might be able to guess then that on this one, when we have that positive charge, that's going to be missing an electron. So when we total up our valence electrons, we subtract 1 from the total instead of adding 1. But on my NO3 here, which, by the way, this is called a nitrate ion. On our NO3 1 minus, we're adding an extra electron, and that is 24 valence electrons. Okay, so let's jump in with coming up with the Lewis structure here. My nitrogen is the least electronegative because it's the farthest away from fluorine, so I'm going to put that one in the middle, and my 3 oxygens around it like that. Right away, I know I need to put in my bonding pairs, and now I've spent 2, 4, 6 of my 24 electrons. That leaves me with 18 to play with. I'm going to go around and give as many octets as I can until I run out. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18. And now I've run out, because that's the 16 plus the original 6 is 24. I was able to give all octets except for my nitrogen, so I need to ask one of my oxygens here to double up like that. And I could have asked any of my oxygens to double up, but I just chose the left one because that's what I always do. Remember from part 2, we talked a little bit about resonance and what that means. Really, because we could have drawn it anyway, like we could have drawn it like this, or we could have put the double bond on the bottom oxygen there. Really, they're all kind of happening at the same time, and like in actuality, we have a sort of a hybrid between all 3 existing at the same time. So it's like 1 1/3 bonds all the way through, instead of 2 single bonds and a double bond. But picking any oxygen is totally fine. If that's confusing to you, just pretend I didn't say it. It doesn't matter that much, honestly, for this class. Oh, one more thing. When we draw Lewis structures for molecules that have charges on them, which, by the way, there's a name for these. These are called These are called polyatomic ions. Nitrate is one example of a polyatomic ion. CO3 2- carbonate is another example of a polyatomic ion. And you might be able to see why. Let me break it down. Poly is more than one, atomic, more than one atom, ion, right? This is a nitrate ion because it's made up of more than one atom, polyatomic, but it has a charge on it, so that's what makes it an atom. Sorry, that's what makes it an ion as opposed to a molecule. Still covalent compound, though. Oh, sorry, I didn't finish my thought. When you draw a Lewis structure for a polyatomic ion, it's not complete unless we draw brackets around it and put the charge up there to show that this compound does have an extra electron, it has a charge, and that's what makes it, I guess that's why we're able to complete the octets. That's just like the grammar of chemistry, like you just got to do that. So don't forget that. CO3 2-, let's go for it. Okay, so we got carbon is 4 plus 6 for my oxygens. I got 3 of them, and then we have a charge of 2-, so that's an extra 2 electrons. Let's see, that's 18, 20, 24 electrons again. And, you know, this is going to be exactly the same as my nitrate. My carbon's going to go in the middle, and I know just because I have the same number of valence electrons, and it's pretty much the same thing going on. We have a central atom with 3 oxygens around it. I know the same exact thing is going to happen. So I'm not even going to spend any more time on that. That's that. This time, though, we do need to put the brackets, and we need to say 2-. Some people will write the minus sign first. If you're writing -2 instead of 2-, I don't really care that much. And this is a carbonate ion. When I was in chemistry, we got a big long list of these polyatomic ions. We had nitrate, carbonate, carbonite, nitrite, hypochlorite. It was I don't know, a list of 12, I think, that we got, and we had to memorize them. And then we got quizzed on it, but times have changed, I guess, since then. I'm not going to ask you to memorize any polyatomic ions. In fact, you're going to get a list of polyatomic ions on any quizzes when they show up. So that's kind of nice. You don't need to memorize the charges or anything. Anyway, C2H2 is the next one. This one is not a polyatomic ion. You can tell because it has no charge up here. So I don't need to add or take away any electrons after I count up my valence electrons here. Let's see. My carbons have 4 each, and I got 2 of them. Plus my hydrogens have 1 each, and I got 2 of those. So that's 8 plus 2 is 10 valence electrons. I know that my hydrogens can never go in the middle, so I'm going to put my 2 carbons in the middle. Like that. And then my hydrogens on the outsides like that. If you're wondering how I knew to do that, maybe you wanted to do something like this. That would be understandable why you'd want to do that. But check it out. Once I start putting in my bonding pairs, there's a problem. This hydrogen is making 2 bonds, and it has 4 valence electrons around it. That cannot happen. There's no room around a hydrogen atom to put 4 electrons. It's just too small. It can't handle them. So this is the only configuration where we have no hydrogen atoms in the middle. Like, they can't be anywhere except the outside, I guess is the better way to say it, rather than they can't be in the middle. Anyway, let's put in our bonding pairs. 2, 4, 6. I have 4 left, which is not that many at all. Okay, and now I'm out. So I've spent 2, 4, 6, 8, 10 of my 10. And this carbon got his octet. He's chilling. This hydrogen has his 2. He's chilling. This guy's chilling. But this carbon is sad. He's only got 4. So let's take those away and make our carbon share them. Now he has his 8. He has 6, so we're closer. And our hydrogens, of course, still have their 2. We're going to have to ask our left carbon here to share again. And make a triple bond there between the carbon and the other carbon. And now we've made all our octets. So we have a hydrogen double bonded to a carbon, triple bonded to another carbon, double bonded to another carbon. And there we go. No brackets this time because it's not an ion. Let's make this smaller. I need more room. Cool. NCS1 minus. NCS1 minus. Okay, so that's a 5 plus a 4 plus a 6. Hopefully by this point you're getting pretty good at memorizing the number of valence electrons per atom, per element. 9 plus 6 is 15 plus another one, and that gives us our 16. Anytime you have an odd number, you're going to run into some trouble. So if you get an odd number, double check your math. You might have added incorrectly. Or if you are doing a polyatomic ion, make sure you remember that extra electron to get you up to that even number. There are some covalent compounds that do have an odd number of valence electrons. I think nitrogen monoxide is one of them. And when we do those, some weird stuff happens. Maybe we'll do that at the end of this video, if I remember. Let's add it in. We'll talk about that in a little bit. But NCS, 16 total valence electrons. Which one is going to go in the middle here? NC and S. Okay, N, C, S. Ooh, this is kind of tricky. Because my carbon is 2 away. My sulfur is 2 away, but one of them is down. So how do you decide which one is going to go in the middle? Well, let me clue you in on a secret here. Carbon is always going to make 4 bonds. It's very rare that carbon does not make 4 bonds. So for that reason alone, I'm going to put carbon in the middle. Yeah, I mean, I guess that's just something you learn. Carbon makes 4 bonds, so I'm going to put the S and the N on either side of it like that. And so when I say it makes 4 bonds, some of those can be double bonds. Like a double bond counts for 2 of those 4. So I know just from that I'm going to be making 4 bonds here. It is a question of whether that's going to be 2 doubles or maybe a triple and a single. I don't know. Let's put in our electron pairs, our bonding pairs, and then we'll talk about it. 2, 4. I have, what, 12 left? 2, 4, 6, 8, 10, 12. Yeah, so this is a predicament, right? Because I can either do a triple bond here and a single bond there, or I could do 2 double bonds, or I could do a triple bond here and a single bond there. So how are you supposed to know? Is that it? Is that done? Yeah, okay, there's all my electrons. So which one is it? So remember, if you watched part 2, then you saw what I talked about with resonance. Technically, all 3 of these do happen to some extent. But the question is deciding which one is the main one. And to answer that question, we need to think about electronegativity and like typical bonding behavior and all kinds of things, I guess. I'm going to be totally honest with you. I do not remember how this bonds. So why don't we do this? Why don't you watch me do some live Googling here? Why didn't that work? Hold on. There we go. That's the one. Okay. What was this? NCS1 minus. I don't even remember what that one's called. NCS1 minus. I can't even type correctly. NCS1 minus. Oh no. Polyatomic. Oh, that's why I wasn't coming up, because I was writing it wrong. This is thiocyanate. That's right. Normally written SCN. I don't know why I wrote it NCS, but let's see. Yeah, that's right. We got to talk about formal charge in order to do this. Okay, so look, you can see that I was correct here. That these are the... What the heck? Just view image. Open image in UTab. Okay. So you can see that I was right? We have the triple bond here, or the triple bond here, or the double bond and the double bond. The way that we decide which one is like the most common is something called formal charge. And I really don't want to talk about formal charge right now, but there is a way to figure it out. Okay, super honesty time. I don't remember formal charge or the rule with it. Let's watch this video together and learn. Hold on. Let me make sure. No, not you. Let me make sure you can hear. You cannot hear. Hold on, wait. Okay, I think you can hear that. If you can't, this is going to be awkward. Okay, that's right. Okay, so the way that we figure out the formal charges on each of the atoms, don't worry about what formal charges for a second, but the way we figure out the formal charge is we count up the total number of valence electrons, subtract those valence electrons that are non-bonding, and then we also subtract the number of bonding electrons divided by 2. That's just the formula that you do, and if we were doing formal charge, you would get really annoyed with calculating it. Calculating formal charge, I guess what you should know about it is that it's a tool for figuring out what's going to be the most stable resonance structure. I'm going to skip through all of his calculations because I don't care. Let's see. Wait. Okay, that kind of makes sense, actually. So because the nitrogen is more electronegative, it makes more sense that the nitrogen would end up with the -1 formal charge. And we can see here, this is the set of calculations for the right Lewis structure here, where nitrogen does have a -1 formal charge here. If this is confusing or dumb to you, just ignore it. But yeah, because in this one the nitrogen ends up with the -1 formal charge, and in this one the sulfur ends up with a -1 formal charge. The -1 formal charge is like more stable on the nitrogen because the nitrogen is more electronegative, which means that it's attracting those electrons more more strongly, I guess. I noticed that he didn't talk about the third Lewis structure, right? The third possibility with the triple bond over here and the single bond over here. But I bet if we were to do it, we would realize that the formal charges were weird. So that's probably why he didn't do it. Okay, so not a huge difference, but a big enough difference that this one is going to be the most common. Anyway, okay, we're kind of got off track here. Let's come back to our drawing here because we got 2 more to do. Wow, okay. So H3O is next, H3O plus. This is called a hydronium ion. This is another one of those polyatomics. Hydronium ion. We can tell that this is like a water molecule that ended up with an extra hydrogen. Some interesting chemistry we could talk about there, but let's just chug right along. 1 valence electron per hydrogen, and I got how many? I got 3, plus 6 from my oxygen, minus 1 because I got a +1 charge here. So I need to lose an electron. That's 3 plus 6 is 9, minus 1 is 8 valence electrons. Like that. Let's put our oxygen in the middle, because it has to be, and then our 3 hydrogens around that. Let's go 2, 4. Remember when I said I wanted this video to be shorter? It's been 23 minutes. Goodness. 2, 4, 6. I have 2 left. We can do that. Easy peasy. Don't forget your brackets and your 1 plus charge up there. Or you can just put a plus. The 1 is assumed. Remember I said chemists are lazy? I wasn't kidding. Okay. Should we do NO? I guess we should. Why not? Let's do it. NO. Nitrogen has 5. Oxygen has 6, sorry, for a total of 11 valence electrons. I got no charges on here, so I don't get to add 1 or subtract 1. We're going to be stuck with that odd number. Let's put our bonding pair right there, and then we have 9 more that we can put. So I can do 2, 4, 6, 8, 9. 2, 4, 6, 2, oh goodness. 2, 4, 6, 8, 10, 11. So that's one way we could do it. What else could we do? We could do 2, 4, 6, 8, 9. There's 11 total. Or we could totally ask oxygen to make a double bond here, right? And now that gets everyone closer. Our oxygen has his octet here. Our nitrogen now has 7, which is better than 6. Or what did it have before? It just had 5 before, so getting up to 7, that's a lot better. So maybe this is what we would go with? What's the difference between these two? Well, in this one, our oxygen only has 5. Let's do this then. Let's say a nitrogen share like that. And now the oxygen has 7, and our nitrogen has 8. So, okay, it's probably one of these. Yeah, where one of our atoms has 7 electrons and the other one has 8, or vice versa. Which one do you think is going to be more stable here? Well, if we wanted to figure it out, we'd have to go and calculate formal charge. I don't really want to do that right now. So, you know what? I'm just going to leave you with that. I'm getting tired and my voice is hurting, so I want to stop talking. Tell you what, why don't you, if you're curious, of course, you don't have to do this, you don't have to do any of this, but why don't you go on YouTube and find the video that this guy made. I'm sure he made one on the Lewis structure for NO, and I'm sure he'll talk about formal charge. And if you're really interested, you can learn more about that. I'm not going to quiz you on it, but it might be a nice little, I don't know, bonus question or something like that. So, I don't know, whatever. If you're interested, do it. If not, honestly, I'm surprised you're watching this far into this video. But there you go. There's a nice 25-minute rant on Lewis structures for those of you who are really interested. The 10 of you, maybe. Okay. That's it for me for now. Yeah. Hopefully I'm not out sick too much longer. Yeah, want to be back at work. Okay, anyway, take care.